Okay, so welcome to the second part of lecture 2. So as I said in the previous part, we are going to look at the necessary and sufficient conditions for arbitrary placement. So what we're trying to look is at this fact: is there a transformation to convert to controllable canonical form? So let us take a general control system state space form, as general as is possible for us at this stage. So it's a seesaw system again, ax plus bu y is equal to cx. There is no drift term, and this system is not in controllable canonical form, right? So let us suppose there is a transformation that can convert the system to controllable canonical form. We have already seen that we can move from one state space representation to another state space representation by doing a similarity transformation. And let us suppose that in this case we have a similarity transformation possible, which is given by x bar is equal to px. And this P matrix is something like, say, P11, P12, P1n. It will be an n cross n matrix, which is going to have a non-zero determinant because it's a basis matrix. So Pn1, Pn2. So this will be Pnn. And I'll also write down this matrix in this form. Let us suppose that the first row of this matrix is P1, the second row is P2, and the last row is Pn, right? So these are the initial entry. These are the entries in individual entries of the P matrix, and these are the rows. So P1 is the first row of P, P2 is the second row of P, and Pn, and so on and so forth. So P is an n cross n matrix, right? And the rows are P1. So P1 row would be 1 cross n matrix, right? Similarly for P2, P3 up to Pn. So when you apply this transformation into this system, you get a transformed system, and this transformation is such that we are assuming that the transformed system that we get is in controllable canonical form. So when you apply this in the when you substitute this equation in this, what you'll get is, we have already seen this before in the first 2 units, x bar dot is equal to P inverse APX plus P inverse BU, right? And y is equal to C P x bar, P inverse x bar, right? So this system is in controllable canonical form. We have assumed this, and we can write this in a compact way like this: x bar dot is equal to a bar x bar plus b bar u, and y is equal to c bar x bar. So you had an initial system which was not in controllable canonical form. You applied this similarity transformation, and you got the system in controllable canonical form, given like this. Now, what is the transformation P that makes this possible, right? And is it possible for all kinds of systems? So let us look at this equation that we have written: x is equal to px, x bar is equal to px, right? So we'll work on this equation and try to find out what kind of P converts a system to controllable canonical form, right? So let us look at the first component of this. If you look at this equation, please remember these are your state matrices. This is the original system which has a description in terms of x, and this is x bar is the new state variable, which is basically a linear combination of the earlier state variables, which were x, right? So these are state variables. So this is an n cross 1, n rows 1 column, state variables n rows 1 column, and this is n cross n. So let me take the first component of this x1 bar. I can write this as P1 x. And why is that possible? Because if you look at this multiplication, let me write it like this. So this is x1 bar, x2 bar, this is xn bar, right? And this is your P matrix. So P11, P12, P1n, Pn1, Pn2, Pnn, right? So this is your P matrix, and this is your X. So what is the first component here? The first component here is equal to this whole thing, this whole row into this whole row, right? So this is what I have written here, that x1 bar is equal to p1x. Now please understand this equation. When you write x1 bar is equal to p1x, what are you writing? You're writing this is a scalar 1 cross 1. This is a row, right? One row n columns, and this is your whole previous state matrix n cross 1. So this is the first component that I'm talking about, and let me differentiate this component. So I get x1 bar dot is equal to p1 x dot, and x dot, if you remember your x dot, it is ax plus bu. Here you have written it. So I can substitute this ax plus bu, and I have p1 outside, right? So I'll write x1 bar dot is equal to p1 ax plus p1 bu. And what is your x1 bar dot? You have already seen, you have already said that your x bar notation, in x bar state variables, your system is in controllable canonical form. So when your system is in controllable canonical form, that automatically means something about x1 bar dot. X1 bar dot has to be equal to x2 bar, right? Because in controllable canonical form, the A matrix, this A bar matrix would be such that the first row is going to be 0 except for the last term, and the B matrix is going to be all zeros except for the last term. So when you say this system is in controllable canonical form, you automatically mean that x1 bar dot is equal to x2 bar dot is equal to x3 bar, and this will go all the way up to xn bar dot, which is going to be equal to xn minus this is going to be a linear combination of, because here in the last equation you'll get all the states. So you'll get x1 bar something into x1 bar. Let us write it more clearly. So let us write for xn minus 1 bar dot. Xn minus 1 bar dot would be equal to xn minus 1 bar, but the last one, the xn bar, would be a linear combination of all the states starting from x1 so it will be, say, a0 x1 bar plus a1 x2 bar will go all the way up to an xn minus 1 bar, plus there will be a u term here in this. So there is no u term in this, but there is going to be a u term in this, right? So this is because of the A matrix that we have, right? The A matrix for controllable canonical form in this case is going to be 0 0 0 1 0 0 last 0, and then you have 0 0 1, and so this is the A matrix, and in the end you have minus a0 minus a1 and minus an minus 1. So because of the A matrix, you can write these equations. Please remember these, because we'll be using them again and again. So what is our x1 bar dot? Our x1 bar dot is x2. So x2 bar x1 bar dot is x2 is equal to p1ax plus p1bu. And you have already seen, because of this equation, that x bar is a linear combination of x's. So you get x bar only by linearly combining x's. That means that x2 bar should also be obtained from the linear combination of only x. So that automatically means that this term has to be 0. This implies that p1b has to be equal to 0, right? And x2 bar has to be equal to p1ax, right? But from the equation here, x bar is equal to px bar, we know that x2 bar has to be equal to p2x, because just like x1 bar was p1x, x2 bar is going to p2x. This here. So x1 bar was p1x and x2 bar would be p2, the second row, into x. Right. So you get two conclusions from this simple mathematics that you have done here. You took the first element, right, and then you differentiated it, the first element from this original equation, you differentiated it, then you applied the fact that your x bar is in controllable canonical form, and because of that you could say that this p1b has to be equal to first thing that you said was x1 bar dot has to be equal to x2, and then because x2 bar is a linear combination of all the x's, so the second term has to be 0, p1b has to be 0, and then you also said that your p2 is equal to p1a, right? So these two conclusions you have drawn from this. Now you take this equation that you obtained here and differentiate this again. So x2 bar dot is equal to p2 x dot. So x2 bar dot is equal to p2. This is very simple. Now you can again write ax plus bu, and you can write p2 ax plus p2 bu, right? And x2 bar dot you can write as x3 bar, because again these x bars are in controllable canonical form. So x2 bar dot you have already seen is equal to x3, right? So when you do this, what you get is we can substitute the value of p2 here. In fact, you can use this equation only and directly put in differentiate this instead of differentiating this one. But in any case, x3 bar is equal to, so p2 is p1a, so you can write p1a square x plus p1a bu. So again, x3 can be a linear combination of only x's, so this p1ab is equal to 0. So this is again your second conclusion, that p1ab is equal to 0. And then since x3 bar is equal to p3x, again from this definition, x3 bar, the third term here, is going to be the third row into this x. So you can write that your p3 is equal to p1a square. So now we can look at the symmetry in these equations. So you get p1b equal to 0, you get p1ab equal to 0, you get p2 is equal to p1a, you get p3 is equal to p1a square. So this is going to continue. You can continue this differentiation and continue it till the second last term. So let us look at the general equation that you'll get. You get something like, see, you're getting, in this case, you're getting you got x2 is equal to p1ax, and then you got x3 is equal to p1a square x. So you'll move this continue this till you get xn minus 1 bar is equal to, you'll get p1 a to the power n minus 1 n minus 2 x. This is from this general formula. So if you continue differentiating, so you get x2 bar is equal to p1 ax. That was the first equation, and then you differentiated this again. Then the second equation that you got was x3 bar is equal to p1 a square x, which you wrote as x3 bar is equal to p3x. But if you took a look at this equation, this one, then you can write xn minus 1 bar is equal to p1 an minus 2 into x, right? And you'll continuously get p1 up. Okay, let us differentiate this one and see what we get. So this xn minus 1 bar dot is equal to p1 an minus 2. That will be x dot. So xn minus 1 bar dot is equal to p1 an minus 2. This is going to be ax plus bu. So it's going to be p1 an minus 1 x plus p1 an minus 2 bu, x bar dot n minus 1. Again, this x bar dot n minus 1 is equal to xn. We have written this here. Okay, we had to write xn here. So this is equal to xn, because x2 bar is x3, xn minus 1 bar dot would be xn. So this is equal to xn, and you can write xn is equal to p1 an minus 1x, and this term has to be 0 because xn bar should only be a linear combination of x's. So if you continue writing these, you'll move up to this place. So p1 an minus 2 b has to be equal to 0. So just like p1b was 0, p1ab was 0, p1 an minus 2b has to be equal to 0, and this equation that you have obtained here, this is pn. Xn bar is equal to pn x. Xn bar is equal to pn, the nth row of this, into x. So you'll write pn is equal to p1 a to the power n minus 1, right? And then you can differentiate this once more. This will be the last equation that you'll get. You write xn bar dot is equal to p1 an minus 1, and in this inside you have x dot, so you'll write it like ax plus bu. So you get p1 nx plus p1 an minus 1 bu. Now in this case, this is the last equation. So in the last equation, you have a linear combination of all the x's. So and there is a u term present. So this term here, this u term here, if you look at this equation, at the last equation here, what is xn bar? Xn bar is a linear combination of all the x bars, and the u term has a 1 here, right? So we cannot comment about what is this p1 a and x going to be, but we can say one thing, that p1 a n minus 1 b has to be equal to 1. So if you collect all this information that you have gathered here on the left half side, right, on the left half side up to this point, what would you write? You write like, starting from here, p1b is equal to 0, p1b is equal to 0, p1ab is equal to 0, up to p1 an minus 2b is equal to 0, but this last term here, p1 an minus 1b is equal to 1. This is one thing that you'll write. So and the other thing that you'll write is p2 is equal to p1a, p3 is equal to p1 A square here. So P3 is equal to P1A square here, and then Pn, this is going to continue. Pn is equal to P1 an minus 1, right? So this information, if you have to write it in a more compact way, you'll say something like this. You'll say P1b, P1ab, P1an minus 1b equal to 0, 0, all zeros, the last one is 1, and you can take this P1 matrix out. This is BAB an minus 1b equal to 0, 0, 1. So if you remember, this is your controllability matrix. We call it, let us say, capital U, a big U, is equal to 0, 0, 1. So you can take the inverse of this. P1 is equal to 0, 0, 1 U inverse. You can take the inverse of this only when U, the determinant of U, is non-zero. And we are talking about a seesaw system, so U is scarce, so you can talk about the determinant of U. So this means that you can do this and you can get a P1, you can obtain a P1 only if your determinant of U is non-zero. That means your system is controllable. Please remember that a system is controllable when the controllability matrix is full rank, or it has rank n if it is not a square matrix. But since it is a square matrix here, as we are talking about a seesaw system, so this implies that the system is controllable. And this will also tell you, if you get P1, you can also obtain the complete P matrix, because the complete P matrix is P1, P2 goes up to Pn. So you have obtained your P1, which is 0, 0, 1 into U inverse, and your P2 is P1A, so that is going to be 0, 0, 1 U inverse, which was your P1 into A, and so on. So this is P1, your Pn is P1A minus An minus 1, so it's going to continue. So this is your transformation. So to conclude, you can convert to controllable canonical form if your system is controllable. That is, it has a controllability matrix which has a determinant which is non-zero, and the transformation that converts to controllable canonical form is given by this equation, where U is the controllability matrix, right, given by B A B a to the power n minus 1 B, right? So to conclude, what you are basically saying is that you can do arbitrary pole placement if and only if, right, if and only if your system is controllable. And you can do this by converting to controllable canonical form if you like, and the conversion to controllable canonical form is given by the transformation x bar is equal to px, where the matrix P is defined like this, right? So basically your original system was x dot is equal to ax plus bu, y is equal to cx. You transform this using this transformation, x bar is equal to px, to a system in this form, x bar is equal to a bar x bar plus b bar u, y is equal to c bar x bar. And this is the system that you got was such that it is in controllable canonical form. And then when you apply the state feedback law, u is equal to minus kx bar on this, you'll be able to arbitrarily place the poles. And what is the state feedback law in terms of the original state variables? If you see u is equal to minus kx bar is actually minus k px. So you have to find the transformation P, right? Find the matrix K by comparing the coefficients like we did previously, and then your state feedback law, which you have to apply to the original system, is going to be u is equal to minus k px. Right? So this is how we do arbitrary pole placement for systems which are not in controllable canonical form. And we have also in the process proven that we can do arbitrary pole placement only to systems which are controllable.